Hello, in this lecture, we will learn more about image classification technology. In this lecture, we will learn about the Caltech 101 dataset and learn about the image classification application of Keras. The Caltech 101 dataset is an image dataset developed in 2003 by California Institute of Technology. This dataset is a dataset designed to be used for image classification technology research and consists of 9,146 images belonging to 101 classes. Unlike MNIST or CIFAR-10 discussed in the previous lectures, the total number of images is small, but it consists of images with much higher resolution. Like CIFAR-10, one image belongs to only one class, and the AI we will be implementing today is also a multi-class single-label classifier like the CIFAR-10 classifier. The original resolution of the Caltech 101 image is the same as what you see on the screen, and it is a size that can be easily recognized by the human eye. In this lecture, we will train a neural network based on the Caltech 101 dataset and classify which image belongs to which class out of 101 classes using the trained neural network. First, we need to download the dataset we will use to train and use our model. Download the compressed file from the following link and unzip it. If you open the folder, there are a total of 102 folders in the folder. If you delete the folder called Background Google among them, 101 folders will be ready. There are multiple images of each class in each folder. In order to use the functions and classes you learned today, you need to install a library called Pillow additionally. Pillow is an image processing library that is a fork of PIL. PIL is an open source image library which was developed until 2011, but since then, the development of PIL was stopped. Unfortunately, the demand for PIL library was still high, and Python continued to be updated after 2011. As a result, PIL had to be updated to support the latest Python 3, and Pillow was branched out from PIL and continued to be developed. And the functions and classes we will learn today also utilize the Pillow library. Activate the virtual environment with Keras installed using Conda. Install Pillow in this environment. This is the code we will write today. Today, instead of designing a model yourself, we will use a neural network model that others have already designed. Keras provides several neural network models that can perform image classification. These models were devised by famous AI researchers, and you can train and utilize neural networks by using these models even if you do not know the design of the neural networks. The code is also available on the course page. Save the code file to the same directory as your Caltech 101 data folder, and run this program from that location. Now, let's explain the first part you see in the code. If you look at the first line, you can see a module called Keras.applications. Keras provides various image classification AI models published through papers in the form of a library. These models are implemented in Keras.applications. We will use one of these models today. If you want to check the various models that exist in applications, please check out the following link. Today, we will use a model called MobileNet among several models. MobileNet is a neural network model developed in 2017 and is a neural network model used for image classification. This model is implemented in Keras.applications. You do not need to know the details of the structure of this model, but since it is a supervised neural network model, The mechanism of this model is similar to the neural networks we have learned so far. In addition to this, various neural network models exist in Keras applications. However, you do not need to know everything about these models. Also, no matter which one of these models is used, the performance difference of the classifier to be built today is not large. But let me explain a little more about some of them. VGG is a neural network model developed at Oxford University, developed as a model that can be used for image recognition in 2015. Keras also supports the VGGNet model. ResNet is an abbreviation for Residual Neural Network and was devised by Kai-Ming He in 2015. This neural network model improved the performance degradation that occurs when the number of layers is increased and has received a lot of attention worldwide. Let's go back to explaining the code. In the 6th and 7th lines, you can see that a class instance image data generator is created. Image data generator is a generator utilized to convert image data to ND-array in real time. In the last lecture, we said that as the size of neural network increases, the amount of training data that can be loaded decreases. The mobile net we'll be using today is much larger than the neural network we've implemented so far. Therefore, the training data we will use today, which is more than 9,000 images, cannot be loaded onto the GPU device at once. Instead, we have to train the model by passing some of the images stored in storage to the GPU little by little. For this, you need to use the generator in Keras. An image data generator is required to make a generator for image data. Data augmentation refers to a technique to create a variety of data similar to the original data by applying a slight transformation to the original data. In the case of an image, you can create images similar to the original image by flipping the image or adjusting the contrast. Keras also provides a function to increase the amount of training data by performing data augmentation when initializing the image data generator instance. But this function will not be used in this lecture. In the 6th and 7th lines of code, the argument of the rescale parameter is passed when the image data generator instance is initialized. If the rescale parameter is set to the initializer of image data generator, the image ND-array is multiplied by the argument value passed to the rescale parameter. In the last lecture, we said that performing normalization will speed up the training of the model. This code is also used to normalize the values inside the image ND-array. The flow from directory method is used to create a training dataset based on the folder name by receiving the parent folder path when images are stored in different folders for each class. The flow from directory method again returns a generator, which loads training data from images stored in a folder. The flow from directory method has a parameter called target size. Target size is a parameter that specifies how to convert the resolution of the image read from the folder. All image classification neural network models and Keras applications have a fixed input size. So if the resolution of the image coming into the classifier is different from the input size of the model, you need to convert the resolution of the image to the input size and then put it into the model. For example, for MobileNet we will use today, the input size is 224 by 224. However, since the Caltech 101 images we have are all different from this resolution, we need to set a target size, convert the image size, and then put it into the model. You can also check the input size of other models on the Keras website. When using the flow from directory method, unlike when using the fit method, batch size must be specified before starting the model training. However, the size of the models in Keras applications to be used today is very large, and the size of the image is also much larger. Therefore, unlike the previous classes, today's batch size must be small. Based on a GPU device with 11 GB of VRAM, batch size can be set to 64. But if your GPU device has less VRAM, please set a smaller batch size. In line 9, the flow from directory method returns a generator. Finally, we made a generator that loads image data from a directory. Now, let's design the model before we start training the model. When initializing MobileNet, the argument of the includeTop parameter must be set to true. This parameter determines whether or not to add a dense layer to the last layer. If you do not pass true to this parameter, the model cannot be trained. So be sure to pass true to this parameter. The models provided by Keras applications are either trained or untrained based on the ImageNet dataset. This time, we will train a classifier that can classify 101 types of images using training data, so the default weight must be set to none. For reference, ImageNet is a large-scale image database, which is used for object recognition technology research. The classes parameter is a parameter that determines the number of classes to be classified by the model. There are a total of 101 types of images in the Caltech 101 dataset to be classified, so the argument must be 101. Calling model.compile method is the same. If you print the structure of the model before training the model, you can see that the model is more complex than the previously implemented model. You don't need to understand this structure. Just be aware that the model is large and consists of several layers. Artificial neural networks composed of many layers are called deep neural networks. Designing these models yourself requires a lot of knowledge and is very difficult, so it is recommended to use models designed by others if possible. When loading training data through a generator, you need to train the model with a method called fitGenerator. If you pass the generator that loads the image data from the directory as an argument, the model.fitGenerator method trains the model. If you check line 14, you can see that the model is trained 20 epochs. Then, the images in the folder are converted to ND-array little by little and input to the GPU device, and the training of the model proceeds. The parameter verbose of fitGenerator is a parameter that also exists in the fit method. The verbose value determines what information is printed to the console during training. The default value of verbose is 1, but it is recommended to set verbose to 2. This is because loss and accuracy are printed every epoch, so there is no problem even if the progress bar is not printed. You can also use the generator when you want to get test data from a folder to evaluate model performance. The evaluateGenerator method shown in the 17th line also receives a generator as an argument, evaluates the model's performance, and returns the performance metrics as a list. In this code, we simply use the entire training data again to evaluate the performance of the model. However, if you want to objectively evaluate the performance of the model, it is better to prepare separate evaluation data. If you have time, search the internet for 200 or more image files for 2 classes, save them, and then train the model. and evaluate the performance of your own image classifier. This is end of today's lecture. In the next lecture, we will learn what computer vision is